This is the title of the problem. We're exploring how the machine learning algorithm, RidgeClassifierCV, short for Ridge classifier with cross-validation, handles multicollinearity, which is when several input features in your data are highly correlated. It's a crucial concept in statistics and machine learning because it can mess up model performance. I'm using SKLEARNLINEARMODELRIDGEClassifierCV, a tool from the SCIKITLEARN library in Python, to classify some data. The problem is my data has lots of multicollinearity. That is, many of my input variables are strongly related. The question asks whether statements about how RidgeClassifierCV handles this are true or false. This statement suggests that RidgeClassifierCV is not the right tool for the job because it's heavily impacted by multicollinearity. I'll need to analyze whether that is indeed true. Here, we are looking at whether RidgeClassifierCV automatically handles the scaling of features in the data, which can impact multicollinearity. I'll need to check if it does it on its own or if I need extra steps. This statement says that RidgeClassifierCV cleverly uses cross-validation, a technique to find the best setting for its internal, alpha, parameter, which helps it deal with multicollinearity. I will investigate its method and correctness. Finally, the statement proposes that using PCA, principal component analysis, a dimensionality reduction technique, before applying RidgeClassifierCV could improve performance. I need to check if this makes sense in the context of multicollinearity. This simply marks the end of the problem statement. This section introduces the core topic: how RidgeClassifierCV, a type of linear model from the SCIKITLEARN library in Python, handles multicollinearity, a situation where your features are too highly correlated. I'll explain whether RidgeClassifierCV is a good choice for such data and what strategies might improve its performance. This tells us we're dealing with a multiple-choice question related to the use of RidgeClassifierCV with multicollinearity. We need to carefully evaluate each answer to determine which are true. This sets the stage for the problem. We are given a scenario. You're using a specific machine learning algorithm, RidgeClassifierCV, and your data has multicollinearity, highly correlated features. The question asks us to identify the true statements concerning this situation. Statement C claims that RidgeClassifierCV uses cross-validation to find the optimal regularization parameter, alpha, aiding in reducing the impact of multicollinearity. This statement is true because cross-validation helps find the best balance in the model, making it less sensitive to correlated features. Statement D suggests that applying principal component analysis, PCA, before training might boost RidgeClassifierCV's performance. This is also true because PCA reduces dimensionality by creating new, uncorrelated features, which can be beneficial when dealing with multicollinearity. I see the core problem here. We're using RidgeClassifierCV, a type of regression, on data where features are highly correlated, multicollinearity. This can mess with the model's accuracy and interpretation. It's like trying to build a house on a shaky foundation. You might get something standing, but it'll be unstable. We need to understand how RidgeClassifierCV behaves under these conditions. This is a multiple-choice question testing your knowledge of RidgeClassifierCV and how it handles multicollinearity. Let's analyze each statement carefully to see which are true and which are false. I disagree. Ridge regression, the heart of RidgeClassifierCV, actually helps mitigate the effects of multicollinearity. It does this by shrinking coefficients, making the model more stable. It's not a perfect solution, but it's not inappropriate. I'll say no to this one. RidgeClassifierCV doesn't automatically scale features. Feature scaling, like standardization or normalization, is a pre-processing step you usually perform before using RidgeClassifierCV, especially if you have multicollinearity. It's like preparing ingredients before cooking, a crucial step for a delicious result. I'd say that's correct. RidgeClassifierCV cleverly uses cross-validation to find the best alpha, the regularization parameter. This helps it balance model complexity and how well it fits the data. This balancing act directly helps to manage problems from multicollinearity. Cross-validation is a good practice because it checks the model's performance across different subsets of the data, preventing overfitting, which is common with multicollinearity. I agree with this one too. PCA is a dimensionality reduction technique. By applying PCA before using RidgeClassifierCV, we can reduce redundancy from highly correlated features, making it easier for the model to learn and improve its performance. Think of PCA as simplifying the problem by focusing on the most important combined features instead of dealing with each feature separately. The big picture. We're looking at how well RidgeClassifierCV, a specific type of classifier, performs when there's multicollinearity, highly correlated features, in the data. Understanding the strengths and weaknesses of RidgeClassifierCV in this situation is key. Okay, let's dive into this. RidgeClassifierCV is a powerful tool, but it's important to understand how it handles multicollinearity. That's when your input features are highly correlated. We'll look at how it works and what you can do to make it even better. This is a multiple-choice question testing my understanding of how RidgeClassifierCV behaves with multicollinearity. I'll need to carefully evaluate each option to determine if it is true or false. I'm given a scenario. I am using RidgeClassifierCV, a type of linear classifier, on a dataset where the input features are very related to each other. The question is testing my understanding of how well RidgeClassifierCV handles this type of data. This statement says that cross-validation helps RidgeClassifierCV deal with multicollinearity by finding the best alpha. Alpha controls how much the model shrinks the feature weights to prevent overfitting. Cross-validation is a great strategy because it helps prevent overfitting the training data and leads to more robust results. So, this statement is true. This statement says that using PCA before RidgeClassifierCV might make it perform better. PCA is a technique that reduces the number of features while preserving the important information. With multicollinearity, some features are redundant. PCA helps to remove that redundancy, potentially improving the model. That makes this statement true, too. I see that you're curious about how RidgeClassifierCV, a fancy name for a type of classifier, handles cross-validation. It's all about finding the perfect balance. The alpha is like a dial that controls how much the model is allowed to be influenced by the data. Cross-validation helps prevent the model from becoming too good at only the training data and not the unseen data. It's like testing your recipe on different groups of people before you launch it. Finding the best alpha via cross-validation makes the classifier more robust when features are highly correlated. I want you to understand that principal component analysis, PCA, is a pre-processing technique to improve the performance of RidgeClassifierCV. Think of your dataset as a messy room. PCA cleans it up by organizing things and removing the redundancy. If you have highly correlated features, like two very similar measurements, PCA can combine these, resulting in a smaller, more manageable dataset that makes it easier for RidgeClassifierCV to focus on what truly matters. This often leads to better performance. Let's dispel a common misconception. You might think RidgeClassifierCV is sensitive to multicollinearity, when features are highly correlated, and would fail. Actually, that's not entirely true. It uses a technique called L2 regularization, which helps stabilize it even with correlated features. It's like having a safety net. It does not completely eliminate the effects of multicollinearity, but reduces their impact, making it suitable. I need to make this clear: RidgeClassifierCV does not automatically scale features. It does not handle feature scaling by itself. Feature scaling, making sure all features have a similar range of values, is a separate pre-processing step you would typically do before using RidgeClassifierCV, especially with multicollinearity to avoid bias. Think of it like preparing your ingredients before cooking. You wouldn't just throw everything into the pot without prepping it first. Imagine you're working with a dataset where many features are highly correlated. This is multicollinearity, and it can cause problems for many machine learning models, particularly those based on linear relationships. This scenario sets the stage for evaluating how RidgeClassifierCV handles this challenge. It's like trying to figure out which ingredient is most important in a recipe where many ingredients are almost identical. Ridge regression is a powerful tool that adds a penalty term to the ordinary least squares regression. This penalty term prevents the model's coefficients from becoming too large, making the model more robust to multicollinearity. Think of it as a stabilizer. It keeps the model from getting too wild when dealing with highly correlated features. This is the core method behind RidgeClassifierCV, which we will be analyzing. I can also see you already know about these concepts. That's amazing. RidgeClassifierCV is a classifier that uses ridge regression internally. We'll explore whether it's suitable for datasets with high multicollinearity, what aspects make it suitable or unsuitable, and whether additional steps can improve its performance in this challenging situation. We'll break down the advantages and disadvantages of using this specific model. Cross-validation is a crucial technique. I use it to assess how well a model generalizes to unseen data. It helps to avoid overfitting by training and evaluating the model on different subsets of the data. In RidgeClassifierCV, cross-validation is used to find the optimal regularization parameter, balancing model complexity with its ability to fit the data well. This is a vital step to make the model robust to the effects of multicollinearity. It's like testing the recipe on different groups of people to make sure everyone likes it equally. Principal component analysis, PCA, is a dimensionality reduction technique. I use it to transform highly correlated features into a smaller set of uncorrelated components. This can simplify the data and remove redundancy caused by multicollinearity, potentially leading to better model performance. It's optional but could be a helpful pre-processing step before using RidgeClassifierCV, especially when data contains strong multicollinearity. It's like simplifying the recipe by removing redundant ingredients. I'm tackling the relationship between RidgeClassifierCV, a machine learning algorithm, and multicollinearity, a statistical problem where predictor variables in your data are highly correlated. I'll explore how well RidgeClassifierCV handles situations with high multicollinearity. I'm dealing with a dataset where the features are strongly related to each other. That's the multicollinearity problem. This makes it harder to determine the individual effect of each feature on the outcome because they're all kind of influencing the same thing. I'm looking at how RidgeClassifierCV uses cross-validation to pick the best, alpha. Alpha controls how much the model shrinks the coefficients. Think of them as weights for features. By doing cross-validation, I can find the alpha value which balances model fit and prevents overfitting caused by multicollinearity. This helps make the model more robust even if my features are highly related. I'm considering using principal component analysis, PCA, before applying RidgeClassifierCV. PCA helps reduce the number of features by creating new ones, which are uncorrelated. By doing this, I can remove redundancy and improve the algorithm's performance. It's like cleaning up your data to make it easier for the model to learn. This is a specific type of classifier, a machine learning algorithm that assigns data points to different categories, that uses ridge regression with cross-validation. Ridge regression is a type of linear regression that adds a penalty to the size of the coefficients, making it less sensitive to multicollinearity. This technique helps to ensure that a machine learning model generalizes well to unseen data. Instead of training and testing on the same dataset, the data is split into multiple subsets, using different subsets for training and testing, and then evaluating performance by averaging the results across multiple subsets. This makes the model more reliable and less prone to overfitting. Regularization is a technique to prevent overfitting by adding a penalty to the magnitude of the model's coefficients. L2 regularization, specifically, adds a penalty that is proportional to the square of the coefficients. This helps to shrink the coefficients towards zero, reducing the impact of highly correlated features. Principal component analysis is a dimensionality reduction technique. It transforms the data into a new set of uncorrelated variables called principal components, which retain most of the important information. This process simplifies the data without losing too much valuable information.